So, our next speaker is Yibo Gao, who's going to be talking about the one-third, two-thirds conjecture for Coxeter groups.
Just give me 1 second. Let's check.
No problem.
Can you all hear me well?
Yeah.
Yes, I can hear you fine.
Okay, thank you. Let me just. Can you see the slides moving? No.
Yes, they're boxed in with the list of the on the right, left and so forth, but I can see them. So
Okay.
if you can't make it full screen, this will do.
I cannot see the slides moving on my end, so I don't know
Oh,
what.
moving. Ah, okay. Sorry. No, they're not moving.
Okay. Sorry about that. Let me just try to. Yeah. Let's just use.
Oh, incidentally, if you have two screens, it might be easier to just unplug one and just work with one single screen.
Yeah. Let me just do this. Can you see the slides moving now?
Now it's moving.
Now, yes.
Okay. Yeah. Thank you very much. Yeah. Okay. Yeah. Sorry about the technical difficulty. And thank you very much, Bruce, for the introduction. And thank you all for coming here. I will be talking about the one-thirds, two-thirds conjecture for Coxeter groups. This is joint work with Christian Gates. When this project was going on, we were both students of Alex Kosinko. So as the agenda, I will first introduce the original one-thirds, two-thirds conjecture, for which I don't know much about, and which is still wide open. Then I will talk about the weak order and convex sets as background, and how to generalize the setting to arbitrary Coxeter groups. Then section 3 and 4 here are interesting special cases that we are able to resolve. And finally, our main theorem says that a uniform lower bound exists for all finite well groups. And we end with some more examples. So a linear extension of a postset is an order preserving bijection from the postset to the n element chain. And we write uppercase E of P to be the sets of linear extensions of P and lowercase e to be the number of linear extensions. For two elements P and Q in this postset, let delta PQ be the fraction of linear extensions such that P appears before Q in this linear extension. So as you can see here, on the numerator, I have the set of linear extensions where P appears before Q, and on the denominator, it is the total number of linear extensions. So this number is always between 0 and 1. And also we know that delta PQ plus delta QP equals 1. And the famous one-thirds, two-thirds conjecture originally formulated in 1968 says that for any finite postset P that is not a total order, there exists a pair of elements PQ such that the delta is between one-third and two-thirds. So here's another way of formulating this. If we define the balance constant B of P to be the max over the pair of elements, and we take the mean of delta PQ and delta QP, then the conjecture is saying that the balance constant is at least one-third. So this number here is at most a half. All right, so why one-third? So this is the prototypical example that achieves the one-third bound. This postset on three elements here has three linear extensions, 1, 2, 3, 1, 3, 2, 3, 1, 2. And if you compute all the delta values, they are all either 0, 1, or one-third or two-thirds. So one-third is the bound for the balance constant. So this conjecture is wide open, but there are many known results. So it is non-trivial that the balance constant is uniformly bounded away from 0. Ken and Linio showed that the balance constant is bounded by 1 over 2e. Ken and Sachs showed that it's at least 3 over 11. Bradwell, Felsner, Trotter improved this bound to 5 minus square root 5 over 10. And all of these results use some arguments involving some log concavity type arguments like the Brute-Minkowski theorem or the Alexandrov-Fenchel inequality. There are also special cases of postset families where the full conjecture, the one-third bound, is known. is known for the width 2 posets, the semi-orders height 2 posets, series parallel posets, and so on. To generalize the setting, let's talk about Commutative groups. And Sarah already talks a lot about them. So hopefully these notions are all very familiar. The Commutative group W is generated by a set of simple reflections S1 through SR, such that we have the relations Si squared equals the identity and Si Sj to the power of Mij equals the identity. Here, Mij can take on any positive numbers that's at least 2, or it can also be infinity. So when Mij equals 2, it means that Si Sj commute. And when Mij equals infinity, it means that there are no relations between I and j. Let L denote the Coxeter length. And the left weak order is defined to be generated by W covered by S times W if the length of W plus 1 equals the length of SW for some simple generator S. Let WS be a Coxeter system. The reflections T are defined to be the conjugates of simple reflections, or the simple generators. The right inversion set of a Coxeter group element W is defined to be the set of reflections such that the length of WT is smaller than the length of W. It's a very useful proposition that says that the left weak Broussard order are exactly governed by the inclusion of the right inversion set. And it's a classical result that the length of W equals the size of the inversion set. We let H be the Hassel diagram of the weak order. And we say that a subset of the Coxeter group is convex if for any 2 elements X and Y in the set, any shortest length path between X and Y remain in C. So this notion of convexity can really be defined for arbitrary graphs. And the graph that we are using here is the Hassel diagram of the weak order. Or in other words, the Cayley graph on the Coxeter group with edges given by the simple generators. And the proposition by Tits says that any convex set C is of the form W sub A sub B, which means the set of Coxeter group elements W whose inversion set contains A and is contained in B. For our purposes, we usually translate a convex set C by some group element W to assume that A equals the empty sets, which also means that it will contain the identity element. So let's look at an example that is the symmetric group Sn, which is a Coxeter group generated by the set of simple reflections I plus 1s. And the reflections are all the transpositions Ij, where I and j are arbitrary. And the reflection Ij is an inversion of W if Wi is greater than Wj. And so here is a picture of the Hassel diagram of the weak order. So I have a convex set C that contains 1, 2, 3, 4, 1, 2, 4, 3, 2, 1, 3, 4, 2, 1, 4, 3, and 3, 1, 4, 2. So if you can see, it's a square plus an edge. So you can see that this set is convex, and you can also write it as C equals W sub empty set sub this set of reflections, which means that none of these 5 elements will have an inversion outside of this set. So for example, these 5 elements will not have an inversion at 1, 3, which means that the first index of all of these elements is smaller than the third index. So for example, here 3, 1, 4, 2, we have 3 less than 4, and here we have 2 less than 4, and so on. For a postset P on n elements, we can, when they are labeled, we can identify its set of linear extensions in a very natural way as a set of permutations denoted C of P. A not hard proposition says that this map gives a bijection between labeled posets of n elements and convex sets of the symmetric group. So this is the example that we just saw for this convex set 1, 2, 3, 4, 2, 1, 3, 4, and so on. And that corresponds to this Postset on 4 elements whose linear extensions are exactly this convex set. It contains 1, 2, 3, 4, as you can see, for example. All right, so why are we doing all of these? Recall the definition. Sorry, is there a question? Okay. So recall the definition that delta Pj Pi is the fraction of linear extensions where Pj appears before Pi. And if we write this in the language of convex sets, that is the fraction of the permutations in this convex set C of P, where Ij is in the inversion set of W. This suggests the following very natural definition. Let C in the Coxeter group be a convex set, and let T be any inversion. Then we can define delta T to be the fraction of the Coxeter group elements which contains T as an inversion. So this number is between 0 and 1. And then we can define the balance constant to be the max over all the reflections T, and we take the mean of delta and 1 minus delta. And remarkably, the natural generalization of the 1/3, 2/3 conjecture still seems to hold for all finite Coxeter groups. So the main conjecture that we have says that let C be a convex set that is not singleton. Then in the finite Coxeter group, the finiteness is very important. Then the balance constant is at least 1/3. So one may argue that there's pretty much an A2 subsystem in any finite Coxeter group that is interesting. So maybe the 1/3 bound just comes from the previous example in A2, where A2 means the symmetric group on 3 elements. So the Postset on 3 elements that you have seen. However, there are genuinely different equality cases that we found in every type not coming from type A. And I'll show you some of these later. For a finite Coxeter group, there's a corresponding Coxeter arrangement. And a convex set here literally means a convex set of regions. And the conjecture says that there's a hyperplane that cuts the convex set into roughly equal parts. So roughly equal means that one part can be almost twice as large as the other part. So in this example here, we have 5 regions, and we can cut it into 2 and 3. So the balance constant here is 2/5, which is greater than 1. The first special case that we are looking at is the fully commutative elements, which are believed to be the critical cases in type A. So an element is fully commutative if no reduced word of W contains a consecutive substring Si, Sj, Si, Sj's, and so on of length Mij, with Mij to be strictly greater than 2. So recall that we have the relation Si, Sj to the Mij's power equals the identity. So if we have Si, Sj of length Mij, then we can change it to Sj, Si of length Mij. And that's a Coxeter move, which is not allowed for fully commutative elements. So for example, in S4, 3, 4, 1, 2 is fully commutative, but S2, S1, S2, S3 is not, because we can apply a Coxeter move to 2, 1, 2 and change it to 1, 2, 1. And so these things are very well known. In the symmetric group, a permutation is fully commutative if and only if it avoids 3 to 1. A related definition is the width of a Postset, which means the longest anti-chain. And under the bijection between naturally labeled Postsets and convex sets in the symmetric group, width 2 Postset P exactly corresponds to convex sets of the form, the interval from the identity to W in a weak order, where W is fully commutative. The 1/3, 2/3 conjecture is known for width 2 Postsets, and we strengthen this result to other Coxeter groups. So our theorem says that let W be a fully commutative element that is not the identity in any Coxeter group W whose Coxeter diagram is acyclic. then we know the balance constant of the interval from identity to W in the weak order is at least 1/3. In particular, this theorem applies to all finite causative groups because their Dynkin diagram are acyclic. So let's look at an example, or rather, this is a non-example. So in the affine well group A3, whose Dynkin diagram is cyclic, then we can take a fully commutative element W, that is S1, S3, S0, S2. And this element is fully commutative, but the balance constant is 2/7. That's smaller than 1. So you'll just have to trust me on this calculation. But the proof of this theorem uses the theory of heaps by Stanbridge, and we are not going into details. So the fully commutative elements give us genuinely distinct equality cases that achieve 1/3. But here I have a table of elements showing you the type, the Dynkin diagram, the fully commutative elements, and their heap posets on the right. So the heap poset is a certain structure whose order ideals correspond to the elements below a fully commutative W. And these posets here are all very different, and that tells you that these examples are in fact different. So the first example in type A2 is the 3-element poset that you saw from the very beginning. The next special case is the semi-orders. A poset P is a semi-order, or also called a unit interval order, if there exists a function f from the poset to the reals such that P is less than Q, if and only if the FQ minus FP is greater than 1. They could also be called, I think, the Heisenberg order or whatever, but they're also very related. Theorem by Bradwell says that if P is a semi-order which is not a chain, then the balance constant is at least 1/3. And we'll be generalizing this result to finite well groups. And this can only be defined for finite well groups, as far as we know. And for that purpose, we need to define the root systems. And this is the axiomatic definition of a root system that I will not go into. I think most people are very familiar with this. But if this is the first time that you see this, then the root system is really just a finite set of vectors in the ambient vector space R to the n, such that they are very, very symmetric in some precise sense. Let phi be a root system. The well group is generated by the reflections across all the roots. In particular, it's a constant. We can partition phi into positive roots, phi plus, and negative roots, phi minus. And given such a partition, there's a unique choice of simple roots, such that each positive root can be written as a non-negative integral linear combination of the simple roots. There's a partial order on the positive roots given by alpha less than or equal to beta if beta minus alpha is a non-negative linear combination of delta. The minimal elements of this poset are all the simple roots, and there's going to be a unique maximum, which is called the highest root in irreducible points. So I have an example in type A. On the bottom, we have the simple roots ER minus ER plus 1, and on top, we have the highest root E1 minus EN. Let W be a finite crystallographic well group, and recall that we have this notation of the convex set W sub A sub B, which means the set of well group elements whose immersion set contains A and is contained in B. We define a generalized semi-order to be a convex set of the form W sub empty set sub B, where B is an order ideal of the root poset phi plus. So it recovers the definition of a semi-order in type A. Let's just recall that a semi-order is defined by P less than Q if FQ minus FP is greater than 1. And let's say our P contains P1 through Pn such that they are ordered based on the F values. Then this set of roots ER minus EJ, where Fj minus Fi is the most one-format order ideal. So if you just think about it a bit more, you'll see that that indeed recovers the definition in type. Our theorem in this section says that let C be a non-singleton generalized semi-order, then the balance constant is at least 1/3. And the proof relies on this purely root theoretic facts that we don't really have a good proof of. So this says that let J be a non-empty order ideal, then there exists a simple root alpha in this order ideal, such that we cannot find two different roots in this order ideal with S alpha applying to them being outside of this order ideal. So it seems like something weird, but it does feel like the correct thing to look at. No proof is type dependent here. Our main result says that the balance constant has a uniform lower bound. Let W be a finite crystallographic well group of rank R, highest through C, and fundamental weights omega I checks, and define those constants that are not really important but will come out of the proof. And the main result says that let C be a non-singleton convex set, and the balance constant is bounded away from 0. So it's at least 1/2 times e to this power, which is at least 1/2 times e to 12th power. So these bounds are really not that bad for the classical types. You can see that for type A, we recover the Ken and linear result. And in type B and C, it's just the same constant. In type D, it's also not that bad. And for the non-classical types, it's not so important because there are only finite in any of them, and they have a finite size. So the proof here uses some Minkowski theorem and some convex geometry. So let me just end with 2 more examples. Recall that the balance constant is at least bounded away from 0 for finite well groups. But there's no universal bound for infinite causative groups. So we let Wn be the causative group whose thinking diagram is a complete graph, which means that none of the generators commute. Then we have this convex set consisting of the identity and all the simple generators. And in that case, the balance constant is 1/n plus 1, which goes to 0 as n goes to 0. There's no uniform lower bound. Also, in the original 1/3, 2/3 conjecture on Postset, it is believed that with2 Possets come closest to violating this conjecture. So with2 Possets corresponds to fully commutative elements, and this heuristic is not true for causative group. So let W be this causative group with 4 generators and pretty high edge weight. So it's not of finite type. Because W is acyclic, we have our theorem saying that the balance constant of this interval below W is at least 1/3, where W is fully commutative. But there are some certain convex sets where the balance constant is 3/10, that is less than 1/3. By the way, this doesn't violate our main conjecture because this causative group is not finite. And that's it. Thank you very much for listening.
Okay, let's thank Yibo for a very interesting talk. And are there questions?
Do you believe that the 1/3 conjecture is correct for any setting after your counter examples to heuristics?
Oh yeah, I still believe that it is correct. It's just it seems that because it is even open in the Postset world, then We just currently don't have enough techniques to really crack the main conjecture.
Other questions? There's one in the chat. Can your theorem on fully commutative elements be phrased as an if and only if statement?
Oh,
this is from
I
Jan
think,
Wang.
yeah, that's a really, really good question. There might still be some parity issue going on, so I don't think that's an easy thing to do at the moment. But this direction, we just know one direction, I should say. Yeah.
Other questions?
So early on, you mentioned that convex sets are a notion that makes sense for any graph, and you're just restricting to some particular nice class of graphs, i.e. Hassel diagrams. Do you have any idea, like, what's so special about these particular Hassel diagrams, or like these particular graphs? Do you think there's a larger class of graphs for which something like the 1/3, 2/3 conjecture could hold?
It's a very good question. I don't have a good sense. I think these graphs are just very symmetric somehow, because you really can't expect this to hold for arbitrary graphs. It'll fail very badly. But I think it really just has something to do with like how the symmetry works, but I don't have a good sense to make it precise.
Other questions? Okay. Oh, here's another one from Christian Stump. Could the conjecture be extended to subsets of the weak order that are closed under intervals? So if two elements are in the set, the complete interval is in there.
I believe that is a convex set. So it should be included.
Yeah, Christian, can you...
I'm not sure if does my voice work here?
Yeah.
My sound?
Yeah.
Okay,
Yeah,
perfect.
thank you, Sam, for answering that.
So you said that the intervals are convex sets.
No.
But take something that's closed under an interval, that's still a convex set?
Okay. Christian said that it's not.
Okay.
Other questions?
Thanks.
Yeah, thanks, Christian, for answering that. Any other questions? Okay, well, let's thank Yibo again.
Thank you.
And